The uniqueness of the Starflex Rotor rests upon the flexibility, resistance, and long life of the glass, carbon, and resin derivate fibrous structure composite materials it is made of. Mastering the use of these materials allowed the realization of an operational rotor made of only 5 basic elements. In a helicopter, the rotor assumes 2 functions: lift and horizontal flight. In order to assume these 2 functions, the rotor must be allowed free play both vertically and horizontally for flapping and dragging. Control of lift and horizontal flight is effected through blade pitch variation. Flapping is the motion of the blade in a vertical dimension. On the Starflex rotor, the star's arms are flexible in the vertical plane. Under the action of flapping forces, the blades drive the sleeve star ensemble. This displacement is effected around the spherical thrust bearings. The drag mode is the motion of the blade within a horizontal plane. The star's arms are rigid in the horizontal plane. The displacement necessary to the drag function is assumed by 2 elastomeric base plates of the frequency adapter. These distort in the scissor mode and permit the oscillation of the sleeve blade and blade system articulated around the spherical thrust bearing. The blade pitch variation is a displacement of the blade around its rotation axis. The star's arms are rigid in torsion. Acted upon by the pitch control lever, the sleeve turns and causes the blade to rotate around its axis while distorting the spherical thrust bearing. In a traditional articulated hub, these functions were assumed by complex systems, including numerous ball bearings and hinges. The principle of the Starflex rotor is the replacement of these mechanical systems of ball bearings and hinges by flexible links taking full advantage of the flexibility of the materials. The Starflex rotor appears within a line of constant improvement. 1955, the turboshaft engine is first applied to the helicopter. 1967, composite blades enter into the industrial production phase. 1967, first shrouded tail rotor. 1975, end product of a constant research towards improved performances, fabrication and maintenance cost, the Starflex rotor consecrates the operational use of composite materials. These plates are made of fiberglass roving, woven glass fibers, wound around the blade's fixation bush. The core is filled with molteprene foam.
Et le remplissage central est réalisé avec de la mousse de molteprène.
The star is made of superimposed layers of fiberglass resin. It has a thick core that includes the housing of the spherical thrust bearing and relatively thin arms shaped in a triangular plane configuration.
Et les bras triangulaires sont d'épaisseur mince qui leur confèrent une faible rigidité en battement.
The laminated spherical thrust bearing is a sandwich of metal cups and thin layered elastomeres
qui constitue un ensemble lamifié, très souple, en torsion et dans les mouvements de battement et de traînée. L'adaptateur de fréquence est
The linkage of the system with the sleeve is secured by 3
dans
bolts.
lequel se trouve la rotule autolubrifiante et assemblée sur les manchons au moyen de 3 boulons.
The blade is a composite. A blade spar made of fiberglass roving, the core made of molteprene foam. The composite blade spar core receives a 4-layer winding crisscrossing at a 45-degree angle. The blade, besides the core and the blade spar, includes a molteprene foam complement. 2 layers of fiberglass make the lining of the blade. The protection of the leading edge is ensured by a stainless steel overlay. The making of the Starflex Rotor is an elaborate industrial process. Witness the blade's construction. From the roving, the mechanical tooling of the spar, the positioning of the foam core, winding of the spar with roving layers crisscrossing at 45 degrees, positioning of the spar in the mold, installation of the leading edge's protective overlay, building of the rear part of the blade, and closing of the mold for baking. The making of a Starflex hub is also the conjunction of the most advanced technologies and the time-proven know-how of the individual craftsman. guarantee a constant quality of fabrication, Aerospatiale turns to highly automated processes such as the computer-programmed laser cutting of the star's fabric. The simplicity of the overall concept saves returning the rotor to the factory for maintenance or repair. The bolted systems, readily accessible, allow for easy mounting and dismantling without specialized tools. All elements of the rotor can be replaced on the spot within less than half an hour. The spherical thrust bearing has only one assembling direction. The assembling direction is indifferent for the self-lubricating ball and the frequency adapter. Only 2 bolts are needed to secure the blade sleeves to the laminated thrust bearing. The blades are attached to each blade sleeve by 2 pins, allowing their folding back. The very long lifespan of the materials and the elimination of lubrication permit the reduction of the number of maintenance operations. This is also due to the fail-safe aspect of the fibrous structure of the materials. Should a deterioration occur, it will not have a brutal and sudden consequence, but the deterioration process will be slow and readily noticeable to the naked eye. The advance achieved by this new generation of rotors is apparent in several aspects. Improved performances, increased payload, higher speed, lower fuel consumption, thanks to the evolutive profile of the blades that can only be obtained by molding. Shock resistance, free of corrosion effects, high performance under stress resulting in unlimited lifespan, increased comfort, very low level of vibrations, reduced exterior noise level, and of course, reduction of the initial cost as well as of the operational costs.